Welcome back. It's lecture 9 time. So, the course on tectonics and geodynamics, lecture 9 will be dealing with something that we touched on very briefly in the last lecture, the concept of triple junctions. And we will be dealing with how triple junctions move around on a flat earth. So, let's just look at what this entails. Right. So, first of all, we'll just mention this particular term that we've used, triple junctions. What are triple junctions? Now, in the context of plate tectonics, a triple junction is the name that is given to a point where three lithospheric plates meet on the surface of the earth. That is what we conventionally call it. Now, in a triple junction, there could be various types. Now, we've dealt with some of these examples in the last class, but what we will try to do is to try to understand how these triple junctions actually evolve. We raised a few questions in the last class, right, in which we talked about how would an observer on the stationary plate observe the boundary between the other plates to be moving. Now, that essentially involves movement of the triple junction between the three plates. So that's exactly what is important. So that is something that we would need to understand exactly what the motion of the triple junction would dictate. So triple junctions, the junctions between any three plates on the surface of the earth, they can be classified into two types, right? So this classification actually could be either as a stable triple junction or as an unstable triple junction. So you could have stable triple junctions or unstable triple junctions. Now, a triple junction, it is said to be stable when the relative motions of the three plates and the azimuth of their boundaries are such that the configuration of the junction does not change with time. Now, these are all words that sound impressive, but exactly what do they mean? So, the idea is that if you have a junction between three plates, let us say something like this. Just imagine that there are three plates A, B, and C like this at one instant in time, and they make angles alpha, beta, and gamma with each other, right? Just for the sake of simplicity. At the next instant of time, right, this geometry will remain identical. So the three boundaries, right, will be oriented exactly in the same manner, and they will make the same angles that they made earlier with each other. So you'd have angles of alpha between this boundary and this boundary, you'd have a beta angle between this one and this one, and a gamma angle between these two. So that means that the three plates, that the relative motions, the azimuth of their boundaries, right, would actually remain the same, the way that the boundaries are oriented around this particular triple junction. So this point is what would be referred to as the triple junction. That remains the same, and this configuration does not change with time. So whatever I'm looking at here, right, so what I'm seeing here, this is really the way it remains, right, over time. So it does not change over time. So now, if I talk in terms of stable triple junctions, then what kind of examples can I think of? So why don't we just think of two of the examples that we've already talked about. Now, let's just think about the last example we dealt with in the last class. So if you remember, we had these three plate systems. You had plate C, we had plate A, I think this was plate B, this was plate A, and we had a subduction zone here. So this was at, if I remember, 6 centimeters per year, and this was a smaller one at the rate of 2 centimeters per year, and this was 4 centimeters per year. So in this configuration of plates, so this is my triple junction, right? This point here is my triple junction. So what is important to me is to understand, let's take a different color to make it a little more colorful. So this is my triple junction. So this triple junction, at this instant of time, if I draw the configuration of the plate boundaries around it, right, the AB boundary is like this, right? So this is the AB boundary. The AC boundary is this way, right? And the BC boundary is just a continuation of the AC line. So this is AC, this is AB, and this is this of course is B and C. Okay, so this configuration, right? So you have one making a right angles with these two. So the AB boundary makes a right angle with the AC and BC boundaries. This is the configuration. Now, as I said, with time, we were thinking of how the system would evolve. And if you remember, what we said was this plate boundary between A and B would move northwards at the rate of 6 centimeters per year, because in this case, it is assumed to be attached to the overriding plate. The overriding plate is moving northwards at the rate of 6 centimeters per year with respect to an observer on plate C. And therefore, this boundary itself will keep on moving northwards. So let's say at some point in the future, the boundary is here. Now, even if the boundary is here, now look at the configuration of the plate boundaries around this the new triple junction position here. So the triple junction actually has moved from here to here. But if you look at the configuration, it's identical. It's exactly the same, except that it's moved a little further to the north. So in other words then, what we have here is an example of a stable triple junction, because the configuration of the plate boundaries around the junction remains identical with time. So the plate motions have operated in such a way that the geometry of the plates, right, the geometry of the plate boundaries around the triple junction remains exactly the same as it was. Therefore, this is a stable triple junction. Now, let's just take an example, take another example here. Okay, since we're doing things colorfully, let's get our colors right. So let's make this the red line. So forget the green line here. So let's take this one, and you remember our old system, the one that we talked about, in which you have a ridge here, right, and this one there. So the ridge spreading this way, you have a subduction zone this way. So this is my plate B, this is plate A, and this is plate C. And if I remember, this is a dextral transform fault, and this is how they would know. So this is another one we were looking at. So in this case, once again, let's make our triple junction green, right, for fun. So this is my triple junction out here. So this triple junction here, let's call it TJ. So the triple junction here is a boundary between two transform faults, one which is actually oriented sinistrally. So this is a sinistral sensor movement here, right? And this is a dextral sensor movement, and there is a trench here. So in this case, right, in all of these cases, we have a triple junction here that is actually a junction between three plates A, B, and C. And we have an orientation which is exactly like this. So although this is a transform fault, this is a transform fault, sorry, this is a transform fault also, and this is a trench, right? So the configuration at the next instant of time, when B actually either grows a little or it moves closer to this particular boundary, nevertheless, the disposition, right, the disposition of the plate boundaries around this point, this remains the same. So if this remains the same, this position, this configuration here also remains the same with time. This is also a stable triple junction, right? So this is also a stable triple junction. That is, with time, right, the configuration of the plate boundaries around the triple junction does not change. This is an example of a stable triple junction. So we have stable triple junctions, right, which can be defined by this kind of behavior. So this will stay, and it will be present on the surface of the earth, right, for a significant period of time. So this is what we understand from the words a stable triple junction. Now let's just move on from here. So we've talked about stable triple junctions. What is the alternative? Well, a triple junction could be unstable. So how do we classify or understand what an unstable triple junction is? Well, the definition is simple enough. A triple junction is said to be unstable, right, when it exists only momentarily before it actually evolves to a different geometry. So in the previous case, we saw that as the plates kept on moving, the geometry or the disposition of the plate boundaries around the triple junction remained the same with time. This is exactly what will not happen, right, if the triple junction is unstable. So when can we call a triple junction unstable? So let's actually go back to our previous example. That was actually a good one. So the previous example, so we'll go back to the one that we looked at last here, and we'll show you what we talk about and we describe as an unstable triple junction. So remember this, right? In this case, we had this three-plate system in which we had a mid-oceanic ridge here, right? We had a mid-oceanic ridge here, and we have this kind of situation here. So we had a ridge spreading this way. This was my sinistral transform fault. This was my dextral transform fault, right? This is my convergent boundary. Now the convergent boundary, right, that's here. So this is my plate B, this is plate A, and this is plate C. Now in the previous case, B was subducting below C. Now let's just think of a situation where now C, this is also remains a convergent boundary, right, as it has to be given these forces, right? But let's say in this case now, B becomes the overriding plate. B becomes the overriding plate and C is the subducting plate. Now, what would happen here? Consistently, as I told you, how would you evolve? So my triple junction here, again, let's make it green. So this is my triple junction here. So this triple junction here, now how will this change with time, or will it change with time? Will the configuration remain the same with time? Now in this case, you see, at this point, these two will not make a difference. So the part that is a transform fault here and the transform fault here, these will be oriented the same way. What will happen is, what is happening to plate B with time? Plate B is produced here at a half spreading rate, which is half the relative velocity of this part here. So this is my half spreading rate. So it is being constantly produced here. And here, there is consumption, but the consumption is of plate C, not of plate B. So plate B, this is the overriding plate. So if this is the overriding plate, plate B is not being consumed at all. So if plate B is not being consumed, then, and it is being produced here, so the particles that make up the leading edge of plate B, these define the position of the trench. Now, the position of the trench remains constant because it is attached to plate B. At the same time, plate B is being produced at a certain rate here. So in other words, if it is being produced here and these particles at the frontal edge of plate B are not being consumed, that means the frontal part of plate B will actually move here with time. So it will move towards the east. So in other words, now this boundary will actually shift, or at least this boundary here will actually continuously shift to the east. Now, as it shifts to the east, you can see what happens is that the previous configuration that you had, which was like this, right? So you had, this was B, this was A, and this was C. So this was the configuration you had. And now the configuration has changed. It's changed such that this is now B, this is now A, and this is now C. The configuration is no longer the same as this. So the next instant of time, this junction will have evolved to a geometry like this. In other words then, now the triple junction orientation, it has not stayed. The distribution, the disposition of the plate boundaries around the triple junction has changed with time. So unlike in the past case, this is an example of what we call an unstable triple junction. So a triple junction in which the disposition of the plate boundaries around the triple junction is changing as a function of time. So at this case now, we've given you an example of what would be an unstable triple junction. Mind you, just keep in mind something quite interesting. We haven't actually changed the relative velocities between the two plates. It remains the same. Nevertheless, all that we've changed is that with the convergent boundary, we've changed we've changed the polarity essentially. So we've converted the previous overriding plate to the subducting plate and the subducting plate to the overriding plate. And what that has meant is that what used to be a stable triple junction has now evolved to an unstable triple junction. Okay. Now, in each of these cases, just mind you, we will use a few terms that are important here. Now, the terms here to do with triple junctions, now let's call this in black. Right? Triple junctions. So a triple junction, you can write it as a combination. Right? So whenever we are talking about the boundary disposition around a triple junction, right, a convergent boundary typically is depicted by the word trench, right, or a convergent boundary. Right? R is the term we use for a ridge or a divergent boundary. It's the letter that we will be using when we are talking about triple junctions to refer to these. And a transform fault is now depicted by the letter F. So if you have a combination, for example, here you have a combination of a trench, you have a combination of a trench, fault, or you can call it a fault, trench. So the triple junction here is two transform faults, right? Two transform faults along with a trench. So we can call it an FFT triple junction, right? So if you can similarly, you can have various combinations. You can have three ridges, so you can have a ridge triple junction. So for example, if I go back one step to the case where we had where was the ridge? Let's go to the I think I've just gone past it. So when we have a ridge somewhere, let's say this ridge. So if this ridge was actually involved in a triple junction, right, then the letter R would actually be a part of the terminology that we are going to use. So let's just shift back now again. So just remember that this is the nomenclature that we would be following, right, when we're trying to talk about the stability of triple junctions. Now let's just go into the next one then. Now we'll talk about evaluating the stability of triple junctions. Now we'll talk about initially a three-plate system. Now let's try to judge. We'll try to evaluate whether a triple junction is to be stable or unstable. And for this, now let's just think of a trench triple boundary. So we've talked about convergent boundaries. So we are talking about trench triple junction. Let's just imagine now that we have a three-plate system, right, like this. Let's say, right, so it's this way. Let us say this is plate A, this is plate B, and let's say this is plate C. Let's say that all of these are trenches, right? All of these triple junctions are trenches this way, right? So let us also just give you a few relative velocities, not the exact magnitudes, but just a gross thing. So this represents the relative velocity of B with respect to A. This represents, let us say, the relative velocity of C with respect to relative velocity of of B with respect to C. This is the relative velocity of B with respect to C. And then let's take this one here, right, to be the relative velocity of C with respect to A. Right. So now the relative velocity of A with respect to B would be just the opposite of this. The relative velocity of C with respect to B would just be the opposite of this, and the relative velocity of A with respect to C would just be the opposite of this, right? So we've got this three-plate system. Now the way I've drawn it, just to make it clear, is that here I have made these convergent boundaries, the boundaries that I have here. So the boundary here, this one, for example, this boundary, I have depicted it in such a way that it has a component of strike slip motion as well, along with the convergence. The same with this particular boundary. On the other hand, the AC boundary, right, the vector between C and A, right, this is exactly orthogonal. Now, what is important for you to note is that in this case, let's look at the three plates in turn. Let's look at the boundary between plates A and B. As you can see, the boundary between A and B, right, is a convergent boundary in which the overriding plate must be plate A because the triangles are pointing this way. So the overriding plate is plate A. Plate B is subducting below plate A. Along this boundary, the boundary between plates B and C, you can see plate B subducting below plate C, right? So plate C is the overriding plate, okay? In this case, plate C is the overriding plate. The third one we have, right, is this one here, in which case that once again you can see that the triangles are pointing towards plate A, which means with respect to the AC boundary, right, plate A is the overriding plate and plate C is the subducting plate. So in other words, plate A, right, is overriding both plates A and C. Plate C is overriding plate B. right? And plate B is actually subducting below both plates A and plate B. So now we have a three-plate system. And now, since we have a three-plate system, we also have this junction, which is our triple junction. So the million-dollar question now for us to answer is the triple junction stable or unstable? What will happen to this triple junction with time? So we know that they are actually separated by stable or unstable boundaries. Now, exactly how do we begin to work out, right, how the stability of this triple junction is going to change? So let us just try to think, right, exactly what this configuration actually means. Now, if let me just erase this and I'll go on to the black one, right? It's a little clearer. So now, as we go on here, right, this is my system, right, if you remember, right, and we have these boundaries here, the boundaries here, the boundary here, right? So this is my plate B, this is my plate A, and this is my plate C. So the velocities were given to us, right, in this particular form, right? So what we are going to now do is to try to assume, right, we are going to attack this problem in a particular way. How do we evaluate whether this triple junction is going to be stable or unstable? So to work this out, now let's do it logically. We'll proceed in a logical sequence. The first thing that we'll do is we will assume that since plate A is overriding plate B as well as plate C, we will assume that plate A is stationary. Let us assume, that plate A is stationary. You must have noticed that I'm trying to be a little more neat in my writing, right? I've always been condemned for my handwriting. So let's assume that plate A is stationary. So we will also say that these boundaries between plates A remain fixed with respect to B and C. So since this is the overriding plate, the leading edge of plate A, right? So the leading edge means this leading edges of plate A, right? The positions of this boundary in this particular square, the overall square I've drawn, right? Within the square, we'll consider it to remain fixed. So this is the frontal edge. The position of the trench between A and B will remain here. The position of the trench between plates, trench between plates A and B will remain here. The position of the trench between plate A and C will remain here, right? So whatever will change will be with respect to plates B and C. Plate A is assumed to be stationary. Now, how do we now logically, I said that we'll analyze this logically, so how do we begin to analyze this logically? So let's now go on to the next way of looking at it. So we'll redraw this diagram again, and although this is a bit of a nuisance, nevertheless it's worth the effort, as you will see. Let's imagine now that we'll draw them, right? So this is by configuration here, right? So we have a little box here, a little part here, right? This is my plate A, this is B, this is C. We have my trenches here, here, and here. And of course, not to forget, right, we had this velocities of B with respect to A, the velocity of B with respect to C, and you have the relative velocity of C with respect to A. Now, to analyze this, I'm just going to do something that is Walt Disney-like. Let's just imagine, right, that all of these plates are made of glass. So we'll imagine that all three plates are made of glass, and so they are moving. We can see what goes on through them, right, behind them. Now, as I've said, I've already fixed the positions. So I fixed the positions of the trenches here. Let's just imagine now what would have happened, like plates A is C. Now let's say that plate A continues to move with respect to plate B because it has this velocity. This is given. So with respect to plate A, this boundary that I've got here, the frontal edge of particles which makes up plate B at this instant of time, they will actually now subduct below plate B. So they will actually move into plate B and it will move with this velocity. So each particle, so a particle here will move here, another one here, another one here. So with the result that ultimately the line of particles, right, that makes up used to make up the frontal edge of particles of plate B at the first instant of time, after some time will actually be in a position here. Now, you can't actually see this line because we should not be able to see this line because it's actually below plate A. So, since I've said that this is made of glass, plate A, we'll just imagine it to be made of glass here. So, since it's made of glass, we can see the frontal edge of particles now of where plate B is now. The edge that was here, the particles that made up this edge, they have actually moved to these positions. So, we know that they are out here now. Similarly, right, if I think of the frontal edge of the particles that make up plate B along this particular boundary, and what happens with respect to plate C? Now, plate C is the overriding plate with respect to plate B. So, where would this be? With respect to plate B, then, this velocity, the velocity that I've drawn here, would move each of these particles this way, and therefore, the position of this boundary between B and C would move here. So, as you can see, this red position that I've drawn here, this actually is indicative. It tells you the new position of the plate boundary between B and C. The frontal edge of plate B is here. I cannot see this here because this is now, I can see this through the glass, but remember that this line is below plate A, and this part of the line is below plate C. Okay, so this is where the line of particles would be. Now let's just go a step further. Let's just look at this particular boundary here. Now this is the boundary here now between plates. This is the boundary here now between plates A and C. Now where would if I now follow how plate C, the position of particles on plate C would actually move with respect to plate A. Obviously, they're moving in this direction. So, therefore, now let's use a different color here. Let's use blue, right? So, the frontal edge of particles, right, they would move because of this. So, each of these would move like this. So, plate C would actually move somewhere. The particles that made up the frontal edge of plate C here, they would now dive under or subduct under plate A to be exact, right? And the particles are now out here, right? So, they can be actually seen here. But with respect to plate B also, since B is moving with respect to C this way, therefore plate C with respect to plate B is moving this way. So each particle would move this way, right? And so the frontal edge of plate C would now be somewhere around here, okay? So the frontal edge of particles that make up plate C are now here, and the frontal edge of particles that made up plate C are here. So the new position of plate C would have been here. The new position of plate B would have been here. If we imagine that we could actually see where the leading edge of the particles that we started off with. So we started off at time t equal to 0, let us say, with all particles here. Now, as we evolve with time, at some later time, the leading edge of the particles that were here along plate B have moved here. The leading edge of particles that were here along plate B and C have moved here, and the leading edge of particles that were along plate C here, these have moved here, along plate the BC boundary here, these have moved here. So now these would be the positions. Since I've assumed that all three plates are made of glass, right? That's just for fun. Because I assume that all three plates are made of glass, therefore we can actually see through and see these boundaries. But now suppose that they're actually not made of glass, right? So if they're not made of glass, well, if they're not made of glass, then in that case, what would we actually see, right? Since they're not made of glass, and of course plates are not made of glass, they're made of solid rock. So what would we see? One thing is for certain. If we now look at the colors that can be visible, let's take another one. Let's take a purple color. So plate A is the one which is overriding. So this is going to be at the top, and the leading edge of particles that makes up plate A, right? The leading edge of particles, that is this part here and this part here, these would fix the position of the trenches visible from the surface. So this is the position of the trench, and this is what is visible to me on the surface. So the position of the convergent boundary is here. So what I will actually see is that the leading edge of the particles are all here, right? So this is the position of the trench. Now this is fixed. So in other words, this part of the boundary, which is the boundary between A and C, which is now below, it lies below plate A, is not visible to me. So I will not be able to see this. I will still see this as the frontal edge. However, now let's take the other boundary, the boundary between B and C. Now you can see that the frontal edge of plate B would have been here. The frontal edge with respect to C would have been here. The frontal edge of plates B with respect to C is here. The frontal edge of C with respect to B is here. But in this case, the overriding plate is plate C. The overriding plate is plate C. Therefore, plate C being solid rock, this part is visible to me, right? This part is visible to me, and I cannot see the position, the new position of plate B here. The plate B bound particles might be here, but I can't see them because they are actually below plate C. Obviously, I cannot see this line of particles either because they are which belong to plate B. We cannot see these because these are under plate A. So exactly what am I seeing? I'm going to see the position of this boundary would be fixed, right? And I will see the position of plate C, the BC boundary would be out here. So what would be the new type of configuration I would see? See if I am to draw it now. So the drawing would be, it would look like this, right? With this being plate A, this being plate B, and this being plate C. So as you can see now, the new geometry that I have, the velocities would remain exactly the same, right? So the velocities would remain exactly the same. The trenches would remain trenches, right? So all these trenches would remain trenches. The only thing that has changed, right, is the configuration. Now look at the configuration that we can see. The configuration is plate A, we assumed it to be stationary, so plate A stays where it is. But you can see that the position of the triple junction now, where was the triple junction? The triple junction was here, and around it, around this triple junction in this diagram, right, you had this kind of sequence. So you had A, B, and C here in this diagram. Now if you look at the new position, what do we see? We see that you have, this is my new position of my triple junction. So in this case, the triple junction is here. This would be plate A, this would be plate B, this is plate C. So this and this evolves to this, right? But obviously this configuration is not the same as this configuration. So this now means then that this is the new position of the stable, new configuration, new configuration of the triple junction, which means then, right, that it's evolved to a different geometry. This therefore obviously means that this triple junction was not stable. It was an unstable triple junction, and now it has evolved to a geometry which is actually very like the example that we looked at. So now it's got orthogonal boundaries like this with trenches here. So now this particular boundary would actually be a stable triple junction. So now we've got it's evolved to a stable geometry. So it moved from here, and the triple junction has moved northwards with time. Now this is the way in which we worked this particular thing out, but it was through logical reasoning. Now logical reasoning is all very fine, it's nice to think of, but is there any simple way, any simpler way we can actually use to solve this problem? Indeed there is actually, but that particular thing involves the use of the relative velocity triangle. So we have to use the relative velocity triangles, and on these triangles we need to put in the orientations of the plate boundaries. So this also has to be put in here. So now On the relative velocity triangles, we need to now somehow put in the orientations of the plate boundaries. Using that, we might find an easier way of trying to work out whether a particular triple junction configuration is stable or not stable. So let's just pull all of this together, right? Let's try to get all this material that we have together. What are triple junctions? These are points on the Earth's surface where three tectonic plates meet. Stable triple junctions, right? A triple junction is supposed to be stable, right, when the relative motions of the three plates and the azimuth of their boundaries are such that the configuration of the junction does not change with time. Okay, that's clear enough. And obviously it is unstable when the triple junction configuration exists only momentarily, right, before it evolves to a different geometry which is expected to be stable. Now, the stability of a triple junction, you can actually determine this by logical analysis of the relative plate motions that we actually did in this class. But there is an easier way, right, in which we can actually analyze this problem using relative velocity triangles. So when we look at triple junctions in the next class, that is what we will do. We will try to examine, right, what kind of principles we can use to find out the orientations or to evaluate the stability of triple junctions. So we are still sticking with Fowler's book. It's still the best one to follow. And on top of that, be prepared and think about what we've talked about. Thank you very much.